Okay. Energy. In this chapter, we will try to cover the energy and we will try to go over different form of energy and explain what kind of and how many form of energy we have and but what is the energy? The energy, what do you think? What is the energy? What we call, why we use the word energy?
Power in an object.
So, energy is something that make the objects move, or energy is something that is about to let the object move. Good. So, for instance, let's say the ball with the mass of m and with the velocity of the v, it's moving. Okay? So what exactly happening? This ball with the mass of m with the velocity of the v has a momentum. Okay? Mass times velocity is going to be momentum. So what exactly happening here? It means that this moving object is transferring energy. What kind of energy? Is a kinetic energy. Good. This moving particle is carrying energy because it does have a momentum. And what kind of energy is a kinetic energy? Okay. And sometime the object is not moving. Okay. The object is not moving, but it does have energy. If that energy released, the object will move. For instance, let's say we have a spring and you compress the spring. Good. When you release, what happened? The spring move. So this energy is called stored energy or potential energy. So it means that the object is not moving, but when you release the object, it will move. Is there any other problem? Any other example that you can just call it a potential energy? Yes, battery. Okay, we call it chemical energy. Good, like chemical energy. In this physics, okay, we mostly talk about the mechanical energy. Yes, that's right. Okay, we have a nuclear energy. Okay, so we have a chemical energy and we have a mechanical energy as well. Okay, so we will be talking in this physics just about the mechanical energy. Good, good.
Uh, called solar panels.
Yes, that's the thermal energy. Good. So energy you receive from the sun, good, and it vaporizes the water or any material. Objects are moving, yes. Thermal energy transfer to the kinetic energy, and kinetic energy transfer to, let's say, electrical energy. That's why, you can just have the electricity. Okay. But what is the other? Because these are a combination of mechanical and then thermal energy. Do you think you can provide any pure mechanical energy, which is the potential mechanical energy or a stored mechanical energy? We have learned in the unit one, okay, that example. You remember the free fall? Okay, so let's say not the glass. Okay, so yeah, this one is better. Okay, so let's say this is a box, yes? What happened if I release? It's moved. What does it mean? It means that the energy is stored in this box. Because when I release it, it's moved toward to the ground. And we call this gravitational potential energy. Good? So we have different form of energy, thermal energy, mechanical energy, and different form of mechanical energy like a kinetic energy, yes? And also potential energy, which is the gravitational potential energy or elastic potential energy for the spring. And this energy sometimes transfer from, you remember we talked about the thermal energy transfer to the mechanical energy and then mechanical energy to the electrical energy. The same thing happened between the mechanical energy. Sometimes potential energy turn into the kinetic energy, sometimes kinetic energy turn into the mechanical, so potential energy, okay? So that's why we call a transformation of energy. Good? Energy is transforming. Okay. Work. What is the work? So let's say you have a box. Good. With the mass of m. Okay. The box is stationary. You exert force on this box based on Newton's second law. What happened? The box will start moving. Okay. And the force that you are exerting on the box that caused the box be transferred d meter. What we say here in physics, we said that we are doing work on the box. If you do work on the box, it means that you are exerting force. By exerting this force, the box is displaced d meter, x meter, 10 meter, 5 meter, thousands meter. Okay? And the definition of the work is force multiplied by distance. Sometimes we call it W equal F D. What is the unit of the force? No, the force. Newton. What is the unit of the D?
Meter.
Meter. So it means that the work unit is Newton meter, or we call it joules. Okay? So again, what the definition of the work is? The box or the particle, you are exerting force. Because of this force, the particle is displaced. And the force is multiplied by the distance the box is traveled, it will be the work. So what exactly happening? Can you explain this with energy? Yes? How?
Find distance that traveled.
Okay, so how you can explain, how many form of energy we have? Mechanical energy, yes? We said that potential and kinetic energy. So what exactly happening? When the box has rest, there was no energy. The box on the ground. Good? No energy, no kinetic energy, nothing. You do the work. What happened? You are transferring energy. See, the work is kind of transferring energy. The box was stationary, it was not moving, no energy at all. You are exerting work on a box. The box will get what kind of energy? Kinetic energy. So, again, you remember the impulse momentum theorem? The ball was stationary, you are exerting force, the ball momentum change. Here, the same thing happening. You are exerting force, you are doing work on the box. The box kinetic energy is changing. The kinetic energy at the beginning was zero because it's not moving. But when you exert force and when you are doing work on the box will get a kinetic energy. Good? So that's why we call it a work energy theorem. Okay. So what is the power? Power is the rate of work over time. Okay? The power is, you have heard the power. You have enough power to lift this box. Okay? What does it mean? It means that, let's say if we have a 100-kilogram box on the ground and you would like to lift this box for 3 seconds and then place it back on the ground. How much power do you need? The work that you need to do to lift the box, yes, over by time. How many seconds you wanna hold it? Let's say 3 seconds. How much work you do? So work divided by time interval is gonna be the power. So the unit of the power is joule per second or watt. So the power is the rate at which energy is expended, and the power is the work done over time interval. So if I write the formula, the power is going to be work over time. We said that the unit of the work is joule. The unit of the time is second. So what is the unit of the power? Joule per second or watt. Okay? Okay. We explained the work, yes? And the work is the form of energy, is the mechanical energy. And what was the work? You are exerting force, and the object is displaced. The work is going to be force times displacement. And one thing which is really important, okay, this example, see? This is an object, okay? I am exerting force, yes? What exactly happening? This object is moving. So the energy, you are transferring energy. You are doing work transferring energy to this box, to this item, and this object or particle is moving. Okay? So right now, I'm exerting force. Am I transferring any energy to the box? Yes or no? What, am I doing any work?
You're holding it down.
Okay. Why? Because this is not moving. As long as there is no displacement, there is no work. I am exerting force, but this force doesn't cause this object move. Sometimes you exert force, the object doesn't move. No work. Those forces that not moving the object, they are not doing any work. Okay? So let's say this object is here, is stationary. We have forces, yes? Normal force and force of gravity. They are not doing any work. Yep. Because these forces are not causing the object move. Okay? So, and if we want to have a work, the force and displacement should be in the same direction. That's how we can have a maximum work. Good? Let's say I have this box, okay? And I'm exerting this force. Definitely this box will move, yeah? So it means that the work is being done on a system. But see here, you remember we used the component of the force. We said that this is a horizontal component, yes? This is vertical component. Instead of just looking at this F, okay, look at these two forces. Good? Because F parallel and F vertical, the resultant is going to be the F. That, as you can see, the F parallel, the horizontal force causing the system to move to the right. This force doesn't do any work. Okay? Because the box is moving to the right. Okay. So just letting you know that the box, or when we are doing a work, so it means that you are exerting a force and the system of the particle or the particle is moving or displacing for the meter. Okay. So mechanical energy. We just said we have two forms of mechanical energy, yes? A kinetic energy and gravitational or potential energy. So first start with the potential energy. We just kind of explain a little bit, but we just explain with more details. So potential energy is the energy, or gravitational potential energy is the energy that is stored on the object. Good. So in this example, you see three balls. Okay. One is, on the top of this vertical path. So this is an inclined path. This one is on the, stairs. So they are all 3 meters above the ground. Okay. When so when you release these balls, what exactly happened? They start to move. So it means that there was an energy stored on these balls, okay? That's why they are moving toward to the ground. Good. And how we can calculate this potential energy? The potential energy, I just show it with PE, is gonna be mgh. What is the m? Is the mass. What is the g? Is the 9.8 meter per second square, is the gravitational acceleration. What is the height? H is the height. And how you can define the height? The height of object from the ground. We always assume that the potential energy on the ground is 0. Good. Let's say you have the box. Okay, so this ball was on the ground. What is the potential energy here? Is 0. Why? Because the height is 0. And what is the height? Height is the distance, or h is the distance of the object to the ground. Okay? We call it height. And the ground is always a reference for potential energy. What does it mean? It means that the potential energy of any object on the ground is 0. Okay? So what is the unit of the potential energy? Again, joule. The same unit for work we use for potential energy. So energy that is stored on the object is called potential energy. Okay. So kinetic energy. We said that any moving object is carrying energy. Let's say we have a ball of a mass of m with the velocity of the v. This moving particle is carrying a kinetic energy. And we just say the kinetic energy is going to be 1 over 2 mass velocity squared. Again, m is the mass in kilogram, and v is the velocity, yes, in meter per second. Any moving particle will have velocity. Any moving particle will have, kinetic energy. And how we can calculate the kinetic energy? Half mass velocity squared. Okay. Again, just review what we have learned so far. So we have object, good, with the mass of m, which is above the ground height. And we said that here the object, when it's not moving, it does have a potential energy, and the potential energy is mgh. Okay? And then we have a moving particle. Let's say it's on the ground. Good. It's not above the ground. This moving particle will have a kinetic energy. How we can calculate? We can just say 1 over 2 m velocity squared. Okay? Good. Example. I have a ball. The velocity is 0. Good. I exert force. What happened when you exert force? The ball move, okay, for d meter. Well, you just, how you can calculate the work? Force times d. Okay, force times this. This ball is moving. Yes, it does have a velocity. Good. So what is the energy here? What kind of energy we have here at the beginning? Kinetic energy, no, at the beginning is not moving. We do have a potential? No. Potential when is the object is above the ground, is about to move. Okay. Do we have any energy here? No. Potential energy is 0, yes? Kinetic energy is 0. So energy is 0. What happened here? Is it still on the ground? Yes? No potential energy. But we have kinetic energy because it does have velocity 1/2 m velocity squared. What exactly happened? You exert force, the object is displaced, and the object received a kinetic energy. There was no energy at the beginning, but the object received kinetic energy. Work is like when you are doing a work, you are transferring energy to the system. The system didn't have any energy. You did the work, you transferred energy to the system by doing work. We call this work energy theorem. Work energy theory. So what does it mean? It means that if you do the work, which is the F times D, what happened? You're just changing the kinetic energy. Good? Or we can say FD is equal kinetic energy final minus kinetic energy initial. Yes? Or I can say FD is equal, what was the kinetic energy at the beginning in this example was 0. Yes? What is the kinetic energy at the final? 1/2 m velocity work energy. Learn the concept, okay? So by doing a work, the object was not moving at it first. By doing the work, you are transferring energy because the object will move. The work that you are doing transfer to the system, the entire work become kinetic energy. Good?
So work and kinetic energy are
No, you are doing work to have a kinetic energy, okay? So you are exerting force, you are doing work on a system, and this work, when it's transferred to the system, is transferred as a kinetic energy. Yes,
So is potential only like if it's dropping?
exactly.
Like if it's just sitting still on the ground, it has no kinetic or potential.
Yes.
But then if you put the work on it, so the tools on it, then it's kinetic.
Yes. Good. If it's underground, because you know the potential energy, whenever the object is not moving and it's above the ground, it means that the object has stored energy in it. It does have a potential energy. It's not moving, but it's above the ground. As long as it's moving, it will have a kinetic energy and potential energy. When we don't have a potential energy, when the object is on the ground. Okay, example. Let's say you are dropping a ball from this height. Yes? The velocity at the beginning is 0. What kind of energy we have? Potential. Why? mg, not is falling because it's above the ground. Okay, it is not moving. Okay, and it's above the ground. Good. Mg is good. Do we have a kinetic energy?
no.
No. So it means that the kinetic energy is 0. 1 second later, 1 second, let's say this is t equals 0. 1 second later, let's call 1 second. What is the velocity from unit 1? Negative 10 meter per second, yes? A times t. A is the gravitational acceleration, okay? So it's going to be negative 10 meter per second. Let's say the mass is 1 kilogram, yes? So right now, the object here, yes? And it does have a velocity of negative 10 meter per second. Good? And what is the height? We don't know, okay, but let's call it h1. Okay? So, tell me, do we have potential energy? Yes or no? Yes. Why? Because it is still above the ground. How we can calculate this potential energy? mg h1. If we did know the h1, yes, let's say h is 10 meter, okay, so this one is, we don't need to provide, okay, the number, okay, because we need to do the calculation more, okay. So let's say h1, what we can calculate. If you say h is 10, okay, you can calculate the h1. So, but we don't. We just, what is important is, okay, we have a potential energy still because the ball 1 second later is still above the ground. Do we have a kinetic energy? Why? It's moving.
Oh, I thought kinetic.
Okay, it's moving. No. It doesn't matter it's moving horizontal or vertical. As long as the particle does have a momentum, it doesn't matter in any direction. It does have a kinetic energy. Good. So we will have a kinetic energy here. And how I can calculate the energy, kinetic energy 1 over 2 mv1 squared. Okay? Let's say 2 seconds later. What is the velocity? Negative 20 meter per second. Good. And then the velocity is negative 20, yes? So do we have a potential and the height is still above the ground, yes? Do we have a potential energy? mgh2. If you had the number, you would be able to calculate the potential energy. Do we have a kinetic energy? Perfect. What is the kinetic energy? 1 over 2m velocity number 2 squared. Good. Which is the velocity here is negative 20 meter per second. Okay? See? I just go step by step. Now, at the end, let's say the box is on the ground. Stop. Before hitting the ground, it still does have velocity. Good? Before hitting the ground, before reaching the ground, and let's say 0.0001 meter, it is still have velocity. But what is the potential? 0. The kinetic energy is still gonna be, let's say, at 3 equal 4. Okay, 4 seconds later. What is the velocity? Negative 40 meter per second. Good. And then we will have velocity, kinetic energy. See what exactly happening? On the top, we don't have a potential energy. We don't have a kinetic energy. We have a potential energy, and the potential energy is the maximum. As you move toward to the ground, the potential energy is increasing or decreasing? Decreasing. See, because the potential is mgh. M is the same M. G is the same G, but the H is at the top is H. It's become H1, H2, H3 until 0. So it means that on the top we have a maximum potential energy. Okay, no kinetic energy. But potential energy decrease, kinetic energy, now we will have a kinetic energy, yes, at this situation. See? Potential energy decrease a little bit. What happened to that energy? It's transformed to kinetic energy. Again, potential energy decrease. How much is decreased is going to transfer to the, it's going to transform to the kinetic energy until potential energy becomes zero and the entire energy transform to kinetic energy.
So is it in inverse?
Inverse, okay, so that's why I was explaining this, okay, right now. Okay, so we have a conservation of energy. Energy conservation. Or mechanical energy. Mechanical energy conservation. What does it mean? So let me just write it down like this. Okay. We call total energy, okay, let's show the total energy with this. Energy. How many form of energy we have? Two. Potential plus kinetic energy, yes? We have a rule in physics, as long as there is no air resistive force, the energy is constant. Energy is going to be the same for any situation. It's going to be constant. Good? Go back to this problem. How can I calculate the total energy? By adding a potential and kinetic energy, yes? How can I calculate the energy 1 second later? By adding potential, yes, and kinetic energy. I said that energy at 1 is equal energy at 2 is equal energy at 3 is equal energy at 4. When you add the total energy, potential plus kinetic energy is always constant. It doesn't matter you are on the top, you are in the middle, is about to hit the ground. Good? The energy is conserved. The total energy is conserved. What is the total energy? Potential energy plus kinetic energy. Okay? So we call this energy conservation. So it means that energy on the top is going to be equal energy on the bottom. It's going to be equal energy at the middle. Okay? Or it's going to be energy at any point. What is the energy? Potential plus kinetic energy. Okay? Okay, so okay. So sorry about this video projector. Okay, so I know that it's flickering. Okay, so they may be able to fix it. Okay. So we talk about the work energy theorem, and we said that when we are doing a work on a system, you are changing its kinetic energy. Good. So work energy theorem is doing work on a system, you are transferring energy. If the object is stationary, if the kinetic energy was zero, after doing the work, the kinetic energy will not be zero, will change because the work is transferring kinetic energy into the system. So, and then we talked about the conservation of energy, and energy cannot be created or cannot be destroyed. It may transform from one form to another form. As I said, okay, this is another example here. What is the person is on the top of this tower. The only energy he has at the top of the tower is a potential energy. Let's assume the potential energy is 10,000 joule. Its kinetic energy is 0 because it's not moving. When it start moving, the potential energy, because the height decreased, the potential energy decreased. If it decreased 7,500, so how much energy is decreased? The potential energy is decreased 2,500. Yes, it was 10,000 at the beginning. Right now is 7,500. How much energy is lost? Potential energy is lost 2,500. These 2,500, okay, transform to kinetic energy. So it means that if you add these two, potential and kinetic, the total energy gain is going to be 10,000 joule. See, what is the total energy here? 10,000 joule. Okay? 10,000. It doesn't matter which location you are. Your total energy is going to be 10,000 because energy is not created or not destroyed. It's transformed from one form to another form. Good? Here, in the middle, potential energy is 5,000. Definitely the kinetic energy should be 5,000 because when you add, the total should be 10,000. Goes until he reached to the ground, okay? What is his potential energy which is on the ground? 0. So what would be the kinetic energy? 10,000, okay? Because the total energy should be 10,000. Make sense? So this is a conservation of mechanical energy. We call it conservation of mechanical energy, and we have the conservation of mechanical energy when there is no dissipative force. For instance, if we have a resistive force or air resistance, we will not have a conservation of mechanical energy. We have a conservation of energy, not conservation of a mechanical energy, because that energy is being lost by the air resistance, is transferred to another form. It can be a thermal energy, okay? But again, if you add mechanical energy plus thermal energy, it's going to be the total energy. The total energy of the entire world is conserved. So it means that if you add a thermal, mechanical, nuclear, chemical energy of the entire world, it doesn't matter what happened to the world, this total energy is conserved. Good? But here we are talking about the total conservation of a mechanical energy. Okay. The next thing that we would like to explain is machine. So we learned about the work, we learned about the energy. Good? So let's say how the machines work. Fuel burn, thermal energy is created, thermal energy is transformed to the mechanical energy, okay? Like kinetic energy, and then the machine start working. Good? So this is a simple machines, okay? For instance, the machine it should not be exactly the machine, okay? Any mechanical tools which doing the work can be considered as a machine. For instance, this pulley, you see, this person is pulling the rope and is lifting the 500 Newton weight, okay? So what exactly this system is? This is a new machine. This person, instead of exerting 500 newtons to lift up this heavy weight, we create a machine, okay? Instead of exerting this amount of force to lift the we need to exert a small force. Good. You see here, FD time FD. What was the FD? FD was work, force time distance. And the work is the change of kinetic energy. Good. So you are changing the kinetic energy of the system here, but the force, but you are exerting a force to just lift up this heavy weight. Good. So that's why we are doing the same work that we are lifting up these heavy objects. So in machine, we have work input and work output. Okay? What is the work input here in this example? Force time displacement. Okay? What is the force? The force that the person is exerting multiplied by the displacement. Okay? You are displacing the rope. So what is the work output? What you are trying to lift? You are trying to lift a big heavy weight. Okay? So what is the force? Is a big force, but there is a small displacement. Okay, so the work input should be all in machines. The work input is going to be equal to the work output. Okay. So for instance, in here you are using, these machines, okay, to lift up this heavy car. You are exerting a small force, but a big displacement is going to be equal to the force of the car or the weight of the car multiplied by the small displacement. Yes? Okay. And if we have machine, okay, each machine will have efficiency. Okay? Let's say you burn the fuel and the thermal energy is created and the thermal energy is transformed to the mechanical energy. But sometimes not 100% of the thermal energy transformed to the mechanical energy. Good. That's why the efficiency, we define the efficiency. We will say that the efficiency, we were supposed to use the 100% of the thermal energy to turn into the mechanical energy, but 90% of the thermal energy transferred to the mechanical energy. What would be the efficiency? Is going to be 90%. Good. So the efficiency is the energy output over energy input. So efficiency, energy out over energy in, or work out over work in. So here comparing a mechanical energy, the kinetic energy with the momentum. We know that the momentum is mass times velocity, okay? The momentum is mass times velocity. How the momentum is changing with the velocity? Linearly, yes? But the kinetic energy here is 1 over 2m velocity squared. How the kinetic energy is changing with the velocity is changing like a squared. That's why we use a parabola equation, okay? So the first graph, it does show how the momentum is changing with the velocity. The second graph shows how the kinetic energy is changing with the velocity. Good? So the second one, the kinetic energy is changing with velocity, is the like a square. So kinetic energy is proportional to the velocity squared, but kinetic energy is proportional to the velocity squared, and the momentum is directly proportional to the velocity. Okay? So let's say if the velocity double, what happened to the momentum? Double, yes? If the velocity double, what happened to the kinetic energy? quadruple, yes? So because the kinetic energy proportional to the velocity square. Okay. Example number 1. So think about this example. The answer is already available. Okay, so just think about this problem. Okay, take a pen, pencil, and just work on this problem. Okay. The second floor of a house is 6 meters above street level. How much work is required to lift a 300 kilogram refrigerator to the second floor? So in this question, you are supposed to calculate the work. Okay, what is the work formula?
And force multiplies distance.
Force multiplied by distance. Good. So the box is on the ground, yes? And how many forces are exerted on the box? You are trying to exert this force, yes? But we know that when you are lifting, there is another force, is the force of gravity, good? Which is equal to the weight of the object. Okay? What is the weight of the object? Mass times g. Okay? What is the mass? 300 kilogram. What is the g? 10. So Fg is going to be how much? 3000 Newton. Okay, these F that you are exerting, let's say this is a 1 kilogram, yes? How much force I should exert to just lift this up? My force should be exactly equal to the weight of this object. If it is less than the weight of the object, the force that I'm exerting is less than the weight of the object, I cannot. Let's say I'm just trying to lift up this table. So how much force I need to exert on this table? This force should be exactly equal or bigger than the force, yes, of this force should be bigger than or equal the weight of the table, yes? So because the force that I'm exerting is not exactly equal to the weight of this table, I cannot lift it up. So here, this force that you are exerting should be at least should be equal to the weight of the object, yes? What is the force then? Equal to the weight of the object. What is the weight? 3000 Newton. Okay, I found the force. So I found the force, which is 3000 multiplied by distance. How much I need to? I need to move it 6 meters above the first level, yes? To the second level. Okay, it's gonna be 6. When you multiply this, it's gonna be 18,000 joules. Okay? But you would be able to solve this with different. You remember that we said that the work is changes of energy? The work is changes of energy. Let me just solve this, okay, with the other method. So the work was equal to changes of energy. Okay? Right now, I have the box on the ground. Good? What kind of energy I have here? No, is on the ground, nothing is exerted. Is on the ground, yes? So potential plus kinetic is, what is the potential? Zero. Is not moving. Kinetic energy is zero. Now I lift it up here, yes? 6 meter above. What is the potential energy here? Do we have a potential energy? Yes, because it's above the ground. How can I calculate mgh? So what is the m? 300. What is the g? 10. What is the h? 6. It's going to be 18,000 joule. Yes? How about kinetic energy? Do I have a kinetic energy? You lift it up, yes? And then stop. Do we have a kinetic energy? No. You know, you lift this up. It's above the ground. Do we have a kinetic energy? It's not moving. Okay, so the kinetic energy is zero. So what is the total energy then? Perfect. So here, the total energy is the PE again plus KE. What is the energy? It's going to be 18,000 joule. Okay? Good? So, the work energy theorem, it says that work is equal to changes of energy. So what I do? E final minus E initial. Okay? What is the E final? 18,000. What is the E initial? 0. Which is going to be 18,000 joule. So you see how we solve this problem? I solve with two different methods. Work is force time displacement. Good. How much force is required to lift this up? This force should be exactly equal to the weight of the box. Yes? And the second method is work energy theorem. Change of energy is going to be equal to work. You need to see how much energy is changed. When the box is on the ground, no energy at all. When the box is above the ground, how much energy we have? The only energy we have is the potential energy. Kinetic energy is 0. Subtract this energy, so it's going to be the work that you need to. Okay, let's move on to the next problem. What is the next problem? John. Example number 2. Yeah, try to work on this problem, please. See what you can do. The answer is available again. It's telling that which produces the greater change in kinetic energy. Exerting 10 Newton force for a distance of 5 or exerting 20 newtons for the distance of 2. How we can again work energy theorem, yes? The work is equal changes of energy or changes of kinetic energy. We need to calculate the work first for both. What is the work for the first one? See here, 10 Newton times 5, yes? So the work is gonna be 50 joule. And then here for the second one, the work will be 20 times 2. It's gonna be 40 joule. And we know that the work is changes of kinetic energy. So which one produce more kinetic energy, more change in kinetic energy? The first one. Okay? Yes. And then move on to the next problem. Number 3. Example number 3. Okay. Please work on this problem. A lever is used to lift a heavy load when a 50 Newton force pushes one end of the lever down to 1.2, the load rises 0.2 meter. Calculate the weight of the load. Okay, so the work input is equal to work output. Good. You are exerting force and to lift up something by using a machine. What is this machine here? Is a lever. Work in is equal to work out. So again, this is an example of a machine. Okay, you are exerting 50 Newton to push one end of the lever down. How much? Okay, so your force is 50 Newton and the displacement because of this force, let's call F1 and F in or D in is gonna be what? 1.2 meter. Okay. And it's telling that calculate the F out. Okay. Let me just change the color. And D out is how much? 0.2. Yes. The work of in should be equal to the work of out. So the work in is equal work out. So F times D in, F times D out. We have all information that we need. 50 Newton time 1.2 is equal F out. We don't know. Time D out is 0.2. Yes? How we can solve this? Fifty times 1.2. It will be 50 times 1.2 will be 60 equal to F out multiplied by 0.2. So what I do, I just divide both sides by 0.2, 0.2. So these two cancel each other. So F out will be 300 Newton. So again, you need to just calculate the work of each force, yes, and then plug it equal to each other and calculate the unknown value. Does anyone have problem with the, the calculation? No? Okay. Let's see. Okay, so okay. Let's do one more problem. Example number 5. Okay. The figure, we don't have the figure. Okay, so the momentum before and after the collision is the same. The kinetic energy, however, is less after the collision than before the collision. How much less and what becomes of this energy? Okay, so I think for this problem, we need to work on question number 4. Let me just check. Okay, this problem, okay, we don't go over this problem, okay, so because you need to look at the book, okay, so you can look at the book, okay, and then you can come back here and then analyze this problem. Okay, let's do what we do. Let me just go here and just explain the energy conservation. Okay. So you remember we talked about the momentum conservation, and we just said that the momentum of the energy is conserved before collision and after collision. So we would like to see what happened to the energy. Okay, what happened to the energy? So now we have two boxes. Before collision, if the box red is moving, what kind of energy we will have? The box red will have kinetic energy. How about the potential? Does have a potential energy? No, because it's on the ground. Okay? So the blue one, if it's at rest, no energy. Good? We can calculate the total energy of the system before collision. What is the total energy? Kinetic energy plus potential energy of the red box plus kinetic energy and potential energy of the blue box. This is going to be energy before collision. Okay? Let's say, let me just change the mass to exactly the same mass. Good. And then velocity to 0. Okay. So what I do here, reset. Okay. I would like to see how the energy is changing. I will run this. Okay, pause. So what is the initial energy? What is the initial kinetic energy for the blue one? 0. Yes. What is the initial kinetic energy for the red one? 250 joule. Okay. So, and the elasticity is perfectly elastic collision. Okay. So what is the final kinetic energy for red? 0. And what is the final kinetic energy for blue? So what exactly happened? The energy is transferred. So energy is conserved. So whenever we have a perfectly elastic collision, the energy will be conserved. The energy is transforming from one box to another box. Transferring from one box to another box. Okay, let me just change the elasticity. I make the elasticity 0. Good. And then reset. Elasticity right now is 0. What do you think? Do you think energy will conserve or not? Mechanical energy. We are talking about the mechanical energy. The energy, as I said, the total energy in the universe, good, is always conserved. But sometimes we are talking about just mechanical energy, because whenever you are doing transforming mechanical energy from one form to another form, some portion of energy is transferred to the environment as a heat, thermal energy. Okay? The total energy of the universe is still conserved, but the mechanical energy is not conserved. Mechanical energy is the potential energy plus kinetic energy. Good? So, here, two cars. One car is at rest, stationary, the other car is moving with the velocity of 50 miles per second. And we would like to have a perfectly inelastic collision. Boom. When it's boom, what happened? Thermal energy, yes? The kinetic energy is transferring to the car, the second car. But because of the collision, because of the friction, yes? And you know, if you just do this, okay, the thermal energy is created. Good. So because of the collision, the heat energy is created and thermal energy is created. And this thermal energy is transferred to the environment. Is not transferring to the second, yes, car. So what do you think here? Because this is a perfectly inelastic collision. The mechanical energy is conserved or not? No. Okay, let's see. Pause. What is the initial kinetic energy? What is the final kinetic energy? What is the initial energy for the blue car before the collision? What is the final kinetic energy? 62. You know, it is 62.5. So what was the initial energy of the red car? 250. But now initial energy is 62.5. Okay. So how much energy is lost? Yes. Good. So, and then these, whatever energy that the red box have, okay, is transferring to the blue one, but the rest of energy will turn into the thermal energy and goes to the environment. That's why the mechanical energy here is not conserved. Yes? Why? What is the total energy here? What is the total energy before collision? I am adding these two. Yes? Energy 0, energy 250. 250. What is the total energy after collision? 62.5 plus 62.5. It's going to be how much? 125. Yes, Joule. How much energy is lost? It was 250. Now it is 125. Okay. So energy before is 250. Energy after is 125 Joule. Yes? Energy is not conserved. So when we have a perfectly inelastic collision, just momentum is conserved. Yes? Energy or mechanical energy is not conserved. Good? Mechanical energy is not conserved during perfectly inelastic collision. And whenever you forget, okay, just bring an example of a car. Okay, two cars, they collide and they stick together and they move. Okay? But in perfectly elastic collision, not only momentum is conserved, but the mechanical energy is conserved as well. Okay? So we are done with today